Let's talk about implicit differentiation, specifically the good, why we use it, the bad, the tedious part, how to use it, and of course the ugly, where really it is, involves, and let's talk about the good part. Implicit differentiation is really just used to find a slope at a specific point of a curve. So if I have a circular curve, I would drive around to find that tangential slope. I would use implicit differentiation. The bad part is it is tedious, or could be tedious. What I want to impress you upon in this clip is that implicit differentiation you can think of as a Russian nested dolls. I have a picture over here, or a rather example here, but later on I'll show you the picture of Russian nested dolls. What I have over here is a differentiation of y cubed. If you think y in terms of a function of x, then dy dx in terms of y in function of x, then it's 3 times y squared. The last part, dy dx, that's where the implicit differentiation comes in. And here's the picture of the Russian dolls. So basically, you keep on dragging the function out and keep on differentiating it as if it's a Russian nested dolls. You keep on taking it apart. All right, that's the brief overview. And here is the ugly part. I leave you to read this definition part of a textbook, a calculus book I have. I personally think the best way to learn any new concept is through examples. Here I have a circle of y squared plus x squared equal to 25, and I'm asked to find the slope at a given point at 3 minus 4, which is in the fourth quadrant. Method 1, I'm going to use the explicit. By explicit, think of x. X is separated. X is no longer together, like your ex-partner, your ex-girlfriend, ex-boyfriend. So you're no longer together, you're separated. So over here, what I need to do is separate my variables first. But since the point is at 3 minus 4, which is in fourth quadrant, I'm going to use the minus curve. And dy dx from here is a little messy, but not too hard. I trust that you can pretty much do it. It's minus half to the power and minus 2x, since I have to take derivative of x squared in addition to take the quadratic derivative first, and simplify a little bit, and I have at the point 3 minus 4 with the value of positive 3, 4. Now let's take a look at with our new friend implicit. Think of implicit as in involved, so you're together. The x and the y's are still tangled, and you're not separated together here. So what we're going to do here, we'll write the equation and we'll just take derivative right on. Okay, so on the left side I have 2x, y squared, remember the example earlier, that's where the trick comes in. When you take a derivative of x, the variable x, since it's implicitly involved with another variable, you have to take the y dy dx one more step. Thus, the Russian nested doll. Okay, so on the right hand side is equal to 0. And from here, it's very easy. We're going to simply plug in the value of what we're interested at, 3 minus 4. And of course, you get the same answer. Now, grand scheme wise, yes, you do save a little bit work, as you can see over here, and about half the work involved if you can remember the nested Russian dolls for the implicit involved. One is nested into the other. All right, let's take a look at another example where it's a little more involved, where I think the implicit will really shine. Okay, here we're given a problem with 2 branches. Since the point of interest is at minus 7 and 0, we're going to take the negative branch. So let's use our new friend over here, nested Russian doll. We're going to use the implicit first, because it's easy, frankly. We're going to take the derivative. Left side is 1, or is a 0, pardon me, and 1. The right-hand side, when I'm writing over here, of course, you have to remember nested doll. So when you take derivative of y squared, you have 2y. The second part, dy dx, is where really important. Think of a nested doll. You have to drag the y out one more time. All right, so this is 2y times dy dx. And the 3, once again, dy dx has to come out one more time. That's the nested part. And from here, it's really straightforward. And minus 0, or minus 7 and 0, we're going to substitute in. Now, the explicit method is a little more involved. Now, over here, once again, explicit means we have to separate the variables. So I'm looking for an equation where it allows me to have y equal to something. Okay, where how I'm going to go about this is the gem, the essence of the method on the right-hand side. Since I know I have to get y into a f of a function of x, what I'm going to use is a little trick. But once you've seen it once, I think you'll remember it. I'm going to use the quadratic equation because as I realize y squared minus 3y minus 7x plus x is in the form of quadratic equation. Oh, I forgot the parenthesis there. As you can see over here, if I express it into the a equal to 1, b equal to minus 3, and c, since it doesn't have any variable y's in it, to me, or as far as when I use the quadratic equation, it becomes a quadratic form of constant. So I'm going to plug those functions in. I have a nasty, messy one, but it's not something you can't deal with. I'm going to plug it in there and clean it up a little bit. I have this 3 plus minus radical 4x plus 37 over 2. Since our point is on the second half, bottom half, we're going to use the minus half to take the derivative. Now, once again, the explicit one in itself, once you have separation of variables, it's a little messy to take derivative, but it's not hard. But I think the hardest part comes in, you have to find expression of the variable y in terms of x. That itself involves so much work. And I think after this example, you'll agree with me that implicit getting involved and stay involved is a better way to go. All right. Not that it's a relationship advice for anyone, but over here, I'm writing that once I take derivative of dy dx, it's a pretty easy one once you can separate the variable. Dy dx comes in and clean it up a little bit. Now you notice on the left-hand side, we did the implicit before. We have a different form. I don't want anyone out there say, wait a minute, those forms look different. So I'll prove later they're actually the same. Okay, so I'll put it on the pink, we'll do it on the left later on. And evaluate minus 7, 0, have the same answer. Now let's take a look at this 2y minus 3. Is it going to be the same as my implicit differentiation? What I do over here, so I'm taking the expression for my y, I'm going to plug it back in to show you dy dx only has really one form. It's actually the same. They just look the same. They just look different, but they're the same. Kind of like water and ice. They look different, but they're both H2O. All right, so from here, I'm just going to do a little tiny proof on the side to convince you. All right, now overall, in the grand scheme of picture, you can see why the implicit method shines so much. It's so much work just to find a form of y equal to some sort of form of x. Just the separating variable part is so much work. Let me see if I can impress you if you're still not convinced why we go about doing the implicit. Here I have a function, because a nice normal function is differentiable. There's no tricks on this function itself. So if we were to find dy dx implicitly, again, I don't have to separate or split y and x away from each other. I can find it at dy dx by using this Russian nested doll, aka our implicit method. 1 is equal to, on the right hand side, I would have 5y to the 4th, 40, and so on and so forth. Once again, remember the dy dx. You do have to take that doll apart one more time to have that dy dx. That is the essence of implicit. Now from here, algebraically, it's pretty easy. I'm just going to zoom it in a little bit or speed it up a little bit. Okay. Now, notice explicitly, there's no way I can separate the variable in form of y is equal to something. This is where the implicit method shines so much. It doesn't care if you can separate the variable or not. The only trick is you have to remember that rational nested doll. So when you get to take dy dx, you do have to take it apart one more time. Other than that, there has no extra requirement. You separate, your budgets and you separate your living room or your spaces at all. It doesn't really care. Okay, this is where implicit shines so much compared to the explicit. All right, I hope this one helps. This is Dr. Phoenix Pan recording from Tucson, Arizona. This is one of a picture that depicted where Tucson looks like at this time of the year. Just gorgeous out there. Please share or comment on this video. Together, we can make math easy again.